Hello everyone and welcome back to number theory. In our last lecture we proved a theorem that goes back to antiquity, but a very powerful theorem, that we proved that there are infinitely many prime numbers. And the proof is definitely within our grasp. I'm not saying that we should be able to think of that idea in the first place, but having seen the proof, we should be able to reproduce it and understand it. But we're going to be doing some more things having to do with primes and composites today. The first thing I want to do, since it takes such a long time to put this table on the board, the first thing that I want to do is to introduce something called the Sieve of Eratosthenes. This device also goes back about 2,000 years. The Sieve of Eratosthenes. Eratosthenes, an ancient scholar in the Greek world, that was the one that came up with this idea. And so that's why it's named after him. And we call this a sieve because this does pretty much what a sieve does. If we don't know what a sieve is, we might think of somebody panning for gold and they're greedy. They don't want to bother themselves with these little tiny specks of gold. They don't want a hunk of gold unless it's maybe about that big. Excuse me. Excuse me again. But these panners for gold are greedy. They don't want to bother themselves with these little tiny grains of gold. So anything smaller than about that, they just want it to fall right through their pan. And so the bottom of their pan sort of looks like this. And any piece of dirt or rock that's smaller than one of these holes just falls right through. And the only thing that's retained in this pan or this sieve are pieces of rock or gold that are larger than these holes. Pieces of rock and gold that are too big to fall through these holes. So essentially the sieve allows the person who's panning for gold to keep the stuff that they want to keep and get rid of all the other stuff that they don't want to keep easily. All they have to do is just shake the pan back and forth, and all of the stuff that they don't want falls through. The stuff that they do want stays in the pan. Our Sieve of Eratosthenes does pretty much the same thing. Notice that we start at 2. But we don't start at 1 because 1 is that very strange number that's neither prime nor composite. We leave the space here for 1, but we don't put 1 down. And if we draw this table, it's probably good to draw it the way that I've drawn it. And just to make sure I don't do something stupid, when I draw the table out, I actually do put a 1 here, and I go from 1 to 10, and then I start the second column, 11 to 20, start the second row, 11 to 20, then do the third row, 21 to 30, and so forth. Essentially, I'm doing it 10 numbers per row. Then I erase the 1. Now, can we go farther than 100? Absolutely. As a matter of fact, it might be helpful in some cases, if we don't have a list of prime numbers, to go from 2 to 200. What this table is going to do is it's going to allow us to find all the prime numbers between 1 and 100. Now, if we extend this table down and go to 200, it will allow us to find all of the prime numbers from 2 to 200. And the design of this table, having 10 columns, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then starting with the next row. The design of this table is fairly important. Having 10 columns allows us to do what we're about to do fairly easily. Now, the first number in the table is going to be prime. So I circle it. That's a prime number. Every multiple of this prime number is going to be composite. 2 times 2 is 4, that's composite. 3 times 2 is 6, that's composite, and so forth. So you know what we do? We just get rid of all of the multiples of 2 other than 2 itself. We go through the entire table. Oh, look at this. This entire row, this entire column contains multiples of 2. Okay, we just got rid of them. Look at this column. This column contains nothing but multiples of 2. Okay, we got rid of that. Same thing with this column. It contains multiples of 2 only. We get rid of it. Same thing with this column, nothing but multiples of 2. Get rid of it. And finally, this column, the same thing. Nothing but multiples of 2. We get rid of it. And the reason that we got rid of all of those columns with multiples of 2 is that we recognize that 2 itself is a prime number. But every multiple of 2 after that is going to be composite because it has 2 as a factor. We started out with a table having essentially 100 entries in it. And we've just eliminated 50 of them. 50 numbers that we knew for a fact were not prime. So after we've got rid of all of the multiples of 2, we look at the number next on the table, and it's prime also. So now we want to get rid of all the multiples of 3, other than 3 itself. Okay, 9's a multiple of 3. 15's a multiple of 3. 21 is a multiple of 3. 27 is a multiple of 3. 33 is a multiple of 3. 39 is a multiple of 3. 45 is a multiple of 3. 51 is a multiple of 3. And believe it or not, 57 is a multiple of 3. Uh, 63 is a multiple of 3. 69 is a multiple of 3. 75 is a multiple of 3. And let's see, 81, yes, that's a multiple of 3. As is 87. 87, that's 3 times 29. 91, no. 93 is, this is 3 times 31. And 99 is a multiple of 3. Now, if we're careful, we can eliminate these numbers much the same way that we eliminated the multiples of 2, because we look at 3, and oh, look at this. In this diagonal, we have only multiples of 3. And here we had 12, and in that diagonal, nothing but multiples of 3. Here we had 52, multiple of 3, and in this diagonal, nothing but multiples of 3. Here we had 81, and in this diagonal, nothing but multiples of 3. Having the table laid out in this way sort of makes it easy to get rid of not only multiples of 2, but multiples of 3 as well. We could have gone, okay, 3, 15, 30, 12, 33, 45, 57, 60, and so forth. Now, let me get rid of this garbage. Now, the very next number on the table is prime, and that's always the case. Once we've eliminated multiples of the previous primes, the very next element in the table is going to be prime. Circle it. 5 is prime. We want to get rid of all of the other multiples of 5 in the table. Well, guess what? This column right here has nothing but multiples of 5. We got rid of them. Now, is there another column on the table that has nothing but multiples of 5? Yeah, there is. There is this column headed by 10. But you know what? We already got rid of it. In this column, we had nothing but multiples of 10. But a multiple of 10 is also a multiple of 5, isn't it? So, we already got rid of this column. We've just gotten rid of all of the multiples of 5. So we go to the next entry on the table after 5. That's got to be prime. And of course it is. It's 7. And we eliminate all of the multiples of 7 on the table. Let's see. 14, 21, 28, 35, 42, 49. This is the next multiple of 7 that we haven't eliminated yet. So 49 we eliminate. And think about it. Prior to working on 7, we had already eliminated the other multiples of the prime numbers. Prior to 7, we had eliminated all multiples of primes smaller than 7. So the only multiples of 7 at this point that we haven't eliminated are those multiples of 7 that have no prime factors less than 7. Those multiples of 7 that have a prime factor of 2, like 14 or 28, we already got rid of those. So here, let's say before I eliminated 49, the only multiples of 7 that are left on the table to eliminate are those multiples of 7 that have no prime factors less than 7. So let's see. The smallest of these would have to be 7 times 7. Okay. Now, the next smallest would be 7 times some other prime number, like maybe 7 times 11. Let's see, 7 times 8, no, 8 isn't prime. 7 times 9, no, 9 isn't prime. 7 times 10, no, 10 isn't prime. 7 times 11, yep, 11's prime. 7 times 11, here's the son of a gun right here. We eliminate it. Okay. 7 times 12, no, 12's not prime. 7 times 13, yeah, 13's prime. What is 7 times 13? 91. "91 is 7 times 13, we get rid of it. Okay. After that, 7 times any larger prime is going to give us something greater than 100. It's not going to be on the table. So we got rid of all of the multiples of 7. Now we go to the next prime number, 11. And any multiple of 11 that has a prime factor less than 11 is not going to be on this table. So that means any multiple of 11 less than 121 is not going to be on this table. Well, this table only went up to 100 to begin with. So this is the only multiple of 11 on the table. And all of the other numbers that are left are prime. All of the other numbers that are left are prime. Now, if we had a larger table, let's say one that went to 200, there would still be some composites to weed out. But all of the multiples on the table, well, all of the numbers on the table are prime. If they weren't prime, then they would have to have a prime factor less than 11, but we've eliminated all of those multiples of the prime numbers less than or equal to 11. These are the primes from 1 to 100. Let's write them down. 2, 3, 5, 7. 11, 13, 17. Let's see, 19, 23, 29. 31, 37. 41, 43, 47. 53, 59. 61, 67. 71, 73, 79. 83, 89. 97. These are the primes between 1 and 100. I'm going to keep them up here on the board for future reference. here's a theorem that we might know if we've had real analysis, or maybe we've seen this theorem in the proof in our Introduction to Advanced Math course. In case we haven't, we'll go through it again. This is a proof that's always done by contradiction. And I'm assuming something that maybe I shouldn't have assumed. I'm assuming that we know what irrational and rational mean. An integer n. So an integer is rational if it can be expressed as the quotient of integers. So n is rational if there exist integers p and q such that n equals p over q. And an integer is irrational if it is not rational. Oh my goodness, I actually fit that in. So an integer is irrational if it cannot be expressed as the quotient of integers. So what we're proving here is that square root of 2 cannot be expressed as the quotient of integers. And we'll do this by contradiction. We suppose, for the sake of deriving a contradiction, that square root of 2 is rational. Then there exist integers m and n, and we can assume not only that m and n are integers, but we can assume that they're natural numbers because their quotient is going to have to be positive. So there exist integers, and we can say natural numbers, m and n, such that square root of 2 is equal to m over n. That's going to be the case if square root of 2 really is rational. If square root of 2 really is rational, then we can write square root of 2 as the quotient of two integers. And since square root of 2 is positive, we can express square root of 2 as the quotient of two positive integers, two natural numbers. And we'll assume that m and n are relatively prime, that they have no factors in common other than 1. And I'll tell you why. I'll tell you why this is a valid assumption. If m and n did have some factor larger than 1 in common, guess what we do? We just cancel that factor from top and bottom, and then m and n wouldn't have any factors larger than 1 in common. So if m and n do have any factors larger than 1 in common, we just cancel those factors out, and what we have left is a numerator and a denominator that have no factors larger than 1 in common. So if m and n aren't relatively prime, we can fix that by canceling the common factors out of top and bottom. So why not just go ahead and assume that m and n are relatively prime in the first place? It's a valid assumption. Now, square root of 2 equals m over n. So this implies if we square both sides that 2 equals m squared over n squared. We just squared both sides. And then I can multiply both sides by n squared. Now, where do I get off saying this? Well, actually, I think this is Euclid's lemma. If it's not Euclid's lemma, it's one of the other lemmas that's, see, close to that. But I think this is Euclid's lemma. No, it's not. Oh, son of a gun. It's not Euclid's lemma. It's the corollary on page 23, corollary 2. No, that's not it either. Oh, son of a gun. Mm-hmm. Well, let's see. Here's what we have. A and B and C. And greatest common divisor of B and C equals 1. Therefore, A divides C. It's not Euclid's lemma, but it's a lemma or a theorem that we've had. Oh, I know the problem. Well, let's look at it this way. I apologize. If a prime number divides a product, then it has to divide one of the factors of that product. Okay. Theorem 3.1, page 40. If a prime number divides a product, then that prime number has to divide one of the factors. So 2 divides m. Oh my goodness. So 2 divides m. then n equals 2 times k for some integer k. So what does that give us? So from the equation 2n squared divides m squared, we have 2n squared equals, well, n is equal to 2k. So I can take 2k and substitute it in here for m squared. And when I multiply that out, I have 2n squared equals 4k squared, which implies n squared equals 2k squared. And since 2 is prime, and 2 divides n squared, that is 2 divides n times n, this means that 2 divides n. The same theorem 3.1 on page 40. Now, this is a proof by contradiction, and when we do a proof by contradiction, we really want the you-know-what to hit the fan. We want something to go bad. And as soon as we see something go bad, we pretty much realize that we've accomplished what we set out to accomplish. Is something wrong? Let's see. 2 divides m, and 2 divides n. See? 2 divides m, 2 divides n. Now, there's something wrong with that picture somewhere. Two is a common divisor of m and n. Hence, the greatest common divisor of m and n is not equal to 1, since there's a common divisor larger than 1. So this contradicts our assumption that the greatest common divisor of m and n equals 1. Now, what caused us to have this contradiction? It was the assumption that square root of 2 was rational. Since the assumption that the square root of 2 is rational leads to a contradiction, the assumption must be false. Hence, square root of 2 is irrational, which is exactly what we were trying to prove. Now that proof was primarily for fun. It's a proof that we should know. It's a proof that we should see at some time or other. And this seemed like as good a time as any to introduce it. We may have seen it already. We may have seen it in our proof class, or if we had real analysis, we may have seen it in real analysis. Now, the next theorem that we have is a very useful theorem for finding prime numbers using the Sieve of Eratosthenes. This is a very useful theorem. If a natural number n is composite, then natural number n greater than 1 is composite, then it has to have a prime factor less than or equal to its own square root. Now, let's look at the contrapositive of this statement. The contrapositive says, if a natural number n greater than 1 has no prime factor less than or equal to its own square root, then it's got to be prime. So guess what? If we're looking for prime factors of n, We start with 2. No, that doesn't work. We start with 3. No, that doesn't work. Okay, we try 5. No, that doesn't work. As soon as we get up to the square root of that number, if we haven't found a divisor of n by the time we hit the square root of n, it's prime. We don't have to try any more cases. So let n be composite. There exist natural numbers, b and c, that are factors of n. Now, let me just mention a special case. If n is a perfect square, we might have the case where b and c are actually the same number. Oh, here comes this catchphrase again. Without loss of generality, we have two numbers whose product is n. They're natural numbers. One of them has to be less than or equal to the other. So we'll just say, if they're not equal, then b is the smaller of the two. Now, when I say multiplying both sides by b, I'm talking about both sides of that inequality. So we multiply both sides of this inequality by b. And remember, b is positive, so we're not going to reverse the sense of the inequality. Multiply this side by b, we get b squared. Multiply that side by b, we get bc. BC, BC, BC. BC is equal to n. I like that. We look at those two sides of the inequality, and then just take the square root. One of these two factors, the lesser one, has to be less than the square root of n. Am I done? I don't think so. You know, I thought I was done, but not quite. I'm trying to prove that any composite number n has a prime factor less than its own square root. When I introduced the factors of n, b, and c, I didn't say that either one of them were prime. I just said, okay, if b is not prime, then it has composite factors, b and c. Well, maybe neither of those are prime. So, oops, I'm not done. By the fundamental theorem of arithmetic, b has at least one prime factor. Now, maybe b is prime, in which case, see, b has at least one prime factor, p. Now, if b is prime, then b equals p. And if b is not prime, well, p is a divisor of b. P is less than or equal to b. Since p divides b and b divides n, comma, p divides n. So, n has a prime factor, p, less than or equal to its square root. Okay, now I'm done. It turns out this is an incredibly helpful theorem. It can save us a lot of time spinning our wheels, doing stuff that we don't really have to do. Yep, take a look at that for a second, and we'll do some examples. 989, okay. Is 989 prime or composite? We're going to take all of the primes one by one, 2, 3, 5, 7, and so forth, and divide 989 by these primes to see if we get another whole number. Well, how many divisors should we try before we give up? Now, if this number is composite, then it has a prime factor less than or equal to its own square root. Oh, 989 square roots, I have no idea, 30 something maybe? $31.4 So if 989 is composite, it has a prime factor less than or equal to 31. So all we need to do is start at 2 and try each of these divisors, these primes, from 2 to 31 to see if any of them are factors of 989. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's 11. And we can eliminate 2. 989 is not even. We can eliminate 5 because 989 does not end in a 0 or a 5. So let's try 3. 989 divided by 3 is 329.66666. Nope. Try 7. 989 divided by 7. 141.285. Nope. Try 11. 989 divided by 11. 89.9 garbage. Okay, nope. Try 13. 989 divided by 13, 76.07. Okay, that doesn't work. Try 17. 989 divided by 17, 58.176. No. Try 19. 989 divided by 19, 52.05, no. Try 23. 989 divided by 23 is 43. Okay. So 989 is composite. Hey, let's try another one. let's see, 691. Let's see, 691. If 691 is composite, then it has a prime factor less than its own square root. What's the square root of 691? 26.28. So if 691 really is composite, then it has a prime factor P less than 26. So, okay. 2 through 23, those are the primes less than 26. Let's try it again. 691, and we can eliminate 2, we can eliminate 5. So 691 divided by 3, 230.33. Okay, 691 divided by 7, 98.7 something. Okay, no good. Divided by 11, 691 divided by 11, 62.81. 1113 divided by 13, we get 53.15. No, that doesn't work. Okay. 691 divided by, let's see, 1317, 40.647. No. We tried 17, that didn't work. Try 19. 691 divided by 19 is 36.368. No. Try again. 691 divided by 23. 30.04. Well, that's it. We divided 691 by all of the primes less than or equal to its own square root. We didn't get another whole number divisor. $691 is prime. Now, just think about the work this saved us. That we didn't have to try dividing 691 by all of the prime numbers less than 691. We only had to go up to the square root of the number that we were testing for primeness. If we don't have a whole number, if we don't have a prime factor less than or equal to the square root of the number that we're testing, then that number doesn't have a prime factor. That number is prime itself. 691 had no prime factors less than or equal to its own square root. That made 691 prime. Here's one of my favorite things. Three, 1 through 9. Homework, page 43, 1 through 9. And in a day or two, I'll have the solutions to that posted on my website. But in the meantime, go over the notes, hit the pause button, take notes like you were in class, and work the homework exercises. Go through the proofs also. Don't just go, yeah, that makes sense. Yeah, that's right. Yeah, that's right. Go through the proofs that we do in class as if you were proving the theorem itself. That will be helpful. Hopefully within a day or two, I'll be back with another lecture on primes. This one has some theorems about how far apart two consecutive primes can be. And also maybe a theorem, an upper bound on how large the nth prime can be. So let's say n is 100. Can we put a bound on how large the 100th prime can be? We may not know what it is, but can we put a bound on it? Yes. So we'll look at those things next time and maybe some other interesting facts about primes. And again, stay healthy, everyone, and stay well.